brainstorming, the last part of EnVision, and this is a brainstorming session on heating, cooling, and motors and controllers. And this brainstorming session is being done differently. It's a truly brainstorming session. This is not going to have presentations. The way we'll do it, that we plan to take up 10 topics. And each of the topic, there will be maximum of 2 slides put. 2 slides will be put, and 2 slides will be put, 1 second, and very quickly in a couple of minutes we'll present the slides. After that there is going to be a discussion. If there are clarification questions, and then we move to the next topic. The first topic that we have taken up is overview and opening remarks, introduction to concept of heating and cooling. What is the motivation for conducting this workshop? Remember that this is on motors and controllers as well on heating and cooling. Heating and cooling today consumes 50% of world's energy. Mukund has given me these numbers, others have confirmed these numbers, so I presume this is right. Now, most of this is dirty energy, fossil fuel-based energy. Motors and controllers consume 46% of world's electricity. First one is energy. Motors, controller, first heating and cooling, all heating and cooling, including industrial heating, including burning of fuel in a steel kiln. All of that is 50% of all energy, not just electricity. Whereas motors and controllers consume 46% of world's electricity. Okay? Now, as we work on climate change, this cannot continue, and this workshop is focused on how can we, number one, do everything using electricity, number two, do everything using green electricity, number three, how do we minimize the energy consumption? Because another point that you will notice is that this is the most inefficient use of energy. In fact, electricity very often is just used to direct heating in coil, which is extremely energy inefficient. So we will be talking about energy efficiency, going all the way green, and using only electricity. That's what we plan to do. And the first session is of course mine. So introduction on concept of heating and cooling and motors and controllers. Can you? So I'm going to put the first slide, and I think is there one more slide? Yeah. Can you put the slide number 2? This is to be presented by me, so I'm going to talk about it. I think we'll start with heating and cooling first, and then come to motors and controllers. One of the, as I pointed out, our first task is from fossil fuel, that is coal, gas and oil, how soon can we move to green electricity for all heating and cooling? But you know, that is not good enough, because if I take an electric kettle, which we use at our homes and offices, 1 unit of electricity produces less than 1 unit of heat. Can we do better? There is something called Carnot cycle. Cools on one side and heats on other. This is a very, very interesting, those of you remember your Carnot cycle, it actually doesn't generate heat or generate coolness. What it does is transfers the heat from one side to another, from one place to another. The place from which it transfers heat, it cools down. The place where it transfers the heat to heats up. And that's how cooling is done and heating is done simultaneously. What does it mean? It means that since you are only transferring heat, if for example there is a pipe like this and there is say 30 degrees centigrade water in the pipe, I can transfer half of the water here this side to 60 degrees centigrade, another half on this side to 0 degrees centigrade. Of course, to do this, to run the Carnot cycle, I'll need energy, and I use electrical energy. Primarily compression and expansion of a refrigerant. That's how Carnot cycle works. It compresses and expands a refrigerant. When it compresses, it heats up, and that water goes to one side. The other side, when it expands, it cools up. That is the water that is taken to the other side. I will need electricity to run that pump, and today it is quite easily possible to generate 4 units of heating and 4 units of cooling using 1 kilowatt hour, 1 unit of electricity. We say that we create a coefficient of performance from 1 unit of electricity, how much units of heating and cooling that I did, 4 units of heating, 4 units of cooling. Actually you will do probably 4 plus units of heat and 4 minus units of cooling. Can't do exactly, but roughly that. So you can get a COP of 8. Transferring heat from one side of a fluid to another using electricity. Of course, then I can use the hot 60 degrees to whatever I want, 0 degree to whatever I want to do. So this is of course a Carnot cycle. It is implemented in using a heat pump or a chiller. Heat pump or chiller does exactly that. Of course, depending on the conditions of operation, the total COP, it may give maybe as low as 4, but 5, 6, 7, 8 is certainly possible, even more is possible. Now, the only thing that it requires is that heat must be fully utilized and cold must be fully utilized. If it is not, if it is wasted, like what we do out here, we have a chiller which gives you 3 units of heating and 3 units of cooling. The heating, then we throw away the heat to the atmosphere. If you are not utilizing it, of course we are effectively not utilizing the COP. But if we can utilize it, and sometimes it is not possible to simultaneously utilize heating and cooling equally, in which case we can put it into a storage. We can heat hot water or chill cold water and use it, then store it, and assuming that you can store it in an insulated tank, then use the hot water whenever I need and cold water whenever I need. So innovative storage can be used to do heating and cooling. In this area, we would like us to become the world leader. So evolving trends, as I pointed out in the slide on this side, is electrification, alternative storage for grid scale, thermal energy storage, heating, cooling, sensible and latent, and digitalization leading to energy as a service, complete digitalizing, managing the whole thing so that you can do that. This also gives you today's cost. Actually the cost is all wrong. For example, diesel today costs 30 rupees per kilowatt hour. Oh, direct heating, sorry. So this is direct heating. So kerosene can be used for 15 rupees. That's what I used to use my stove when I came to IIT Madras. And then diesel, electricity is 8-9 rupees per kilowatt hour, etc. Biomass is the lowest cost. Coal is there, even is only slightly higher, but remember that all this is highly polluting. So this is the concept that we want to do, and today's workshop, first part of the workshop is on heating and cooling, second part of the workshop is in motors and controller. Remember, you need a motor and controller to do heating and cooling. heat pumps or chiller will require motor and controller. So first part will be done largely by Satya, will lead the thing, and we will focus on heating and cooling. How can we use heating and cooling both together? And this is going to be discussed by Satya Seshadri. We'll put two slides together, or only one slide is there, or second slide? Yeah, two slides.
So
there. And
this
we're supposed to introduce it, then we are supposed to discuss it.
okay. So as Professor Ashok said, this gives a little bit more clarity on how you get those 4 or 8 or 7 units. If you can see, it's basically an air conditioning cycle. So it's not something that none of you know heat pump, you are quite familiar with it. Typically this is what you use in your air conditioners or refrigerators at home. Most of the time we are interested in the area where it is the blue thing called the evaporator, where the temperature is lowered. But as you lower the temperature, energy balance tells us that you need to throw it out somewhere. And we normally throw it out in the ambient. Now how a heat pump generally works is, you tap both of it. While you are using and cooling a space, you also recover the heat. So that's entirely what we do, and the energy balance is completely tied up, it adds up, so there is no violation of any kind of thermodynamics here. The typical challenge is that we normally design it for one or the other. We generally design an AC or we design a heat pump for heating. Now if you want to design it together, if you want to use both together, the challenge is there is two things. One is there is no concurrent demand. So when you need the cooling, you may not need the heat, or when you need the heat, you may not need the cooling. So it's very little concurrent demand of heating and cooling. Second is, as you can already see, you have a lot more heat than the cooling, that means than the demand itself. So as you cool a space in a place like Chennai, when we are looking at applications where cooling is predominant, there is a much larger amount of heat available. Now how do you use it effectively that you can achieve the COP of 7 or 8? Otherwise you still have to reject some amount of heat. Now the second is, while we are looking for concurrent demand, there are two types of applications, right? One, we are looking at commercial, like complexes like these and kitchens and hotels and all, where we understand we do need heat for kitchens, we do need heat for bathing and a few other applications. Some cases there is also need of heat for dehumidification, primarily to remove the humidity from air. But if you want to make this a lot more widespread, we also need to look at the industrial applications. In the slide on the left, you can see.
I can put that slide there.
Huh.
So you can change the slide back.
So now you can see here, across industries, across the space, most of manufacturing that requires heat. Particularly, a good way to look at it is whenever manufacturing deals with any material containing carbon as a material, most of the time the requirement is low grade. Heat temperature is less than about 250 degrees. Many times it's less than 150 or 160. And similarly, there is a free cooling that is getting generated. So if we look at heating as an opportunity, I have put in a few examples of industries that you are familiar with: dairy, food processing, textile, pharma, automotive, brewery. These are all the processes. So in each of these industries, if we look at whatever names that are there or the processes that go into the industry, they all need heating. There is no manufacturing without heating. And similarly, in those places, you also need cooling. In textile, for example, if there is no humidification, the threads break and you cannot get a good amount of textile. So all of this is currently being used. How is it being used? You have a boiler that generates the heat, you have a chiller that generates the cooling. So that is double the amount of energy that is required from an inefficient source. This is clear? Now the question is, how and why this is not taking forward, and what do we do to really push it forward? The first and foremost opportunity is for us to design systems together.
In addition to integrating heating and cooling, could there also be a +1 case for compression? Let's say in addition to doing only these two, can the excess electricity or can the equipment be also used for, let's say, air compression? Can it also be used for, let's say, moving air, for example? So are these the only two dimensions, or should we also look at additional dimensions as well?
So anything else you can always use.
So the way you look at any processing is through 5 utilities. Electricity is the prime one, then heating, cooling, air and water. So these are 5 primary utilities with which any manufacturing and any processing is done. So these are 5 independent equipment. So now what we are saying is that electricity being the prime one, you use that to drive everything else. Heating and cooling becomes one set, compressed air becomes the second set, from which heating is again available, because when you compress something, some heat is available, then water. So from this you don't do any compression, because this already is a compression cycle. If you go back to the other slide here, it already runs through a compression cycle, and it is a closed loop refrigerant. So it is not air that you use.
Agree. Yeah.
Yeah.
This is not theoretical. This is something that we can do today.
And we already do. I mean, in many cases, even if you don't call it and recognize it, it is already being done. It's just that you are dumping one part of it. All the huge cooling towers that you see, it's just dumping the heat. Now what we are looking at is a tight integrated design of all of these elements, and by prioritizing and by designing applications carefully, that it can use it.
Also, for example, having a hot water pipe, clean hot water for my cooking, if I can get at 60 degrees, something like this is not available.
The definition of a heat pump does not require heating and cooling to happen together, right?
Heat pumps
Always.
No, as an that I understand because of energy balance.
So you can use or not use.
That I understood, Professor. But during the introduction, you said heat pumps. No, the application definition is not that, right?
No, the way you imagine heat pump from a very basic pumping perspective, it pumps heat.
That's all.
And anytime you pump it, it's from a low potential source to a high potential source, which is from the cooled surface to cooled area to the hot area. It's against the natural flow. Now the whole discussion here is that how can you effectively use all of it, because you are consuming energy to pump, and how effective is that consumption?
I don't know why. I think the simpler heating and cooling using Carnot cycle, heats on one side, cools on
That's
the other side.
understood, Professor.
You can always throw half the energy.
That's what is happening everywhere.
You can, that's what you do. But if you don't, you can use both of that. That's the way your coefficient of performance or efficiency can be increased. Your efficiency, if you use heat and cooling simultaneously, you are straight away doubling. But if you can do 4 units of heat and 4 units of cooling, you are increasing by 8 times. Far more than your motor otherwise can do. This is a very fundamental concept. And I think not well understood. I didn't understand it a couple of years back.
Professor Satya,
It doesn't sink in easily. People don't understand.
help me understand the previous term, no?
Huh?
It's not yet settled in my mind. How did you evacuate 2 kilowatt of heat?
Okay. So then that brings to your Carnot cycle.
Yeah, please.
Now what does happen in Carnot cycle? Carnot cycle is, how does electricity does heating and heating? It does by passing electricity through a coil.
Okay.
That's a resistive heating.
Okay.
It does nothing like that.
Mhm.
It has a pump.
Mhm.
It runs the pump.
Mhm.
What it does is when it runs the pump, it
Compresses.
compresses something.
Mhm.
Now we are compressing a refrigerant.
Mhm.
When a refrigerant is compressed, it heats up. Temperature will go to 70 degrees, 60 degrees, more.
Mhm.
Now we let the 60 degrees come this side. We are compressing here, we heat, let it come this side, let it flow this side. As it flows, it passes the heat to whatever it wants. There is a what we call condenser or heat heat exchanger. It can heat up the water, or heat up the air, or heat up anything. And it then continues to pass like this. It's a pump and compressed. As it passes, comes here, I suddenly do expansion. It's already cooled down to some extent. As I do expansion, it's already in a vaporized form. So it opens up like anything and cools. It will cool to 0 degree. If it has, and now this side, I cool my water or cool whatever air. Come back here, I again compress again heat.
And
This is what a Carnot engine is.
This is
Am I right?
understood.
Satya, one second, let me finish this. And this 1 unit of electricity, because I am not doing heating and cooling, I am just compressing, I can do 6 units of heating and 6 units of cooling. 6 kilowatt hour of heat, 1 kilowatt hour of electricity, I can do 6 kilowatt hour of heating and 6 kilowatt hour of cooling. So I get 12 kilowatt hour of heating and cooling from 1 kilowatt hour of electricity. I know it's a difficult concept, people don't fully understand, and I'm very happy that it is sinking into your head.
Now, there's one comment Professor Ashok made with regards to the grade of energy. So, while we are using kilowatt hour for all, the kilowatt hour of heat in terms of its ability to do work, which in the case drive a motor, is not the same as a kilowatt hour of electricity. So, the grade is lost. So, that is where from an energy perspective, they are all balanced out. And the energy where it comes from is primarily the fundamental thermodynamic property. So, here, as he said, this is liquid and it vaporizes, and whenever something vaporizes, it has a lot more, it's like boiling water. So, there's a lot of energy that goes in boiling. And when you compress it and then you convert it to liquid. So, again, from a vapor, it's coming back to a liquid. So, again, it gives out a lot of energy. But these are low grade energies, and the reason why we are using it, because that is what we need. So, when we look at this other slide, when we say I want different kinds of temperature, it's not something that is obtained by a single fluid all the time. So, I play with the fluid. So, if you need 100, I use something else. If you need 50, I use something else. So, that's where the system that is used for a cooling of this building is not the same system that I will use for.
Only the refrigerant changes. Mechanism.
Architecture is exactly the same.
Mechanism doesn't change.
And motors do play an important role, because most of my inefficiencies in that system also comes from motors.
If I make that very efficient, I could probably get 14 units of heat.
So right now probably you would have seen in advertisements inverter air conditioners and all. It's primarily playing with the motor efficiency of those systems. Compression is one part, but then it's also to do with
it doesn't use the half the
we are always reject
half
it.
the energy is being put away. Okay? You have a
reclarification.
take better we can do it.
So essentially you are saying, say for example, if there is an apartment, every apartment is using individual refrigerator and AC. Remove all of them, have one thing common, so that you use that one for the refrigeration.
Each have a refrigerator. Except refrigerator will be designed differently. It will take the chilled water and flow. Every appliance will be different, except it will not do heating and compression.
So
compression.
they are throwing out the heat energy that you collect and then use it for a different purpose.
Exactly.
See, you can imagine this in the case of dairy very, very easily. For example, you have a process which does pasteurization. You heat it all the way to about 75, 76 degrees and then cool it back to 4 degrees. Right now for heating you may use a boiler, and for cooling you are using a chiller, whereas both is available simultaneously to you when you run a heat pump. It already heats to about 75, 80 degrees, and I already provide 4 degree, I can provide 4 degree cooling. So it makes a lot of sense if you understand how each of these industries are categorized. I mean, they always use these. Take the example of brewery. You have these malt brewing that happens at 80, 85 degrees and then again cooling to 4 degrees.
I think we are ready to redesign our lives and industry over the next 25 years. We can improve the energy efficiency probably by a factor of 4.
That's certainly possible. Yeah.
Can we think of the reverse of it, like use the concentrated solar power to heat some refrigerant and then use that for cooling subsequently?
No, you can't bring external
See,
energy.
It is just reverse of what we are thinking, because heat energy is available. Instead of converting it with the solar cells in electricity and then back to driving the compressor, you can remove that one conversion itself, and that will be saving of efficiency.
So it's mainly the pressure that drives the whole thing rather than the temperature.
Okay.
If you really look at it, the compressor actually drives the pressure. It's about the pressure that really makes it well. And given, I mean, I have done this math, so concentrated solar or any kind of solar thermal along with PV, if you look at the conversion factor with a heat pump, it more or less works out to be the same, except that solar thermal becomes a lot more complex. PV, it's extremely simple because once you electrify, you can use it any which way. So the heat pump becomes a primary system. Even when solar PV is not there, it still runs on electricity. But when you depend on thermal, then you become a secondary system. So the next section are about three things. One is what's the holy grail, or how much more can we push this technology as it exists, and what are the current challenges. To do that, I have three.
So first of all, COP is coefficient of performance, which is the from 1 unit of electricity, how many units of heating and cooling we can do. And what we have put there, can we do 10 or 12 from 1 unit? And he's saying yes, how? Okay.
So to do that, we need to understand three things. One is currently what are we using it for? One is the max high and max low temperatures in heat pumps and chillers. In terms of maximum, we have 120 degrees centigrade, which goes into commercial heating. And cooling, normally the HVAC system, we use it at about 7 degrees. Marginal improvements you can get by improving efficiencies using different refrigerants. But the current challenges are that some of them are flammable and high pressure. The second aspect of it, what is the current challenge that's involved in increasing the efficiency? One is selection of refrigerants and availability of compressors. That's a critical element because the entire architecture depends on the choice of compressor. The third thing is what I call as high lift. The technical, very simple difference is what's the difference between the cold temperature you have and the hot temperature you have. The bigger the difference, the lower the efficiency. So if you can maintain it to as low as possible depending on your need, exactly matching with your need, then the COPs goes higher and higher. The third aspect of it is tightly integrating. So here I want to bring in this whole concept where when we say I want to cool this room, there are two kinds of processes happening. One is you are removing the latent heat, which is nothing but the humidity in the room, and then actually sensibly cooling the temperature where you go from 25 to 24 to 23. But the latent heat is about removing the moisture in the room. The current refrigeration system does both. It cools down, the coil temperature here is actually much lower. That's why you have a constant dripping of water outside. It does both. But the most sensible way to do it is, can I remove these two? So the current most efficient 10 to 12 COP system tend to separate these two. They use the latent heat removal mechanism separately and sensible cooling. Of course, that material is called desiccant. These are called hybrid systems where you combine all of these to deliver the most efficient machine. Currently not yet fully commercial, but there are some pilot developments, but it really requires us to understand the entire system design as a whole.
Point that is making that yes, with a little bit of engineering and ingenuity, it is possible for us to do the coefficient of performance of 10 to 12, which basically means that from 1 unit of electricity we can do 10 units of or 12 units of heating and cooling.
Yeah, I didn't understand how you will decouple the humidity reduction part and the temperature reduction.
So these category of materials called desiccants, which actually absorb the humidity from air. So it's like silica gel, but there are much better materials that dehumidify the air. And then you only cool the air. So when you actually want to only sensibly cool the air, for a place like Chennai, almost 70% of the air conditioning load is for dehumidification in tropical places. So we actually are mostly paying for all the water that is removed from our body and all of these conditioned spaces. That's the maximum load on ACs. Rest of it is for sensible cooling, and that's why I had made some calculation I can share that, which says if you have an inverter or all of those ACs, it doesn't really matter here because most of the time we are only dehumidifying. Particularly when you keep your room at 27 degrees air conditioner on, it's only removing the moisture. So when you remove it, now you can combine, for example, we are talking about heat pumps, right? Cooling is happening on one side, but I'm also rejecting the heat. Now that desiccant actually can be regenerated using that rejected heat. So right now for a home, when I don't have enough heat, and I already told you that we have more heat we produce than we need. Now if there is a way by which I use all the heat for cooking, cleaning, washing, I still be left with more heat than what I need. That is what I will use for the latent heat removal. So if I can tightly integrate, that's what I said, this tight system integration. If you are able to do that in a very integrated manner, you can actually achieve far higher efficiency than what we can currently do.
So extra heat, how will you use? Can you give an example?
So
Removing moisture?
take the example of calcium chloride or any salt. If you simply leave it open in the atmosphere, it absorbs all the moisture and becomes liquid. So it actually dehumidifies air. Now if I want to regenerate that calcium chloride salt, I have to heat it to reject the water. Now where does the heat come from? I use it from my rejected heat from my heat pump itself. And there are better materials. Calcium chloride is one example. Any material you see, there are a lot of material that absorbs the moisture.
The second point.
The lift, high lift. See, the efficiencies of these heat pumps or chillers that we are talking about, it is based on what is the difference between the evaporator and condenser. Now, he talked about when I want only to work only as a chiller, I only need a 20-degree difference. But if you look at all our current chillers, they actually have a 50-degree difference. Most of our compressors that you see, even though you reject outside only at 40 degree, 45, 50 degree, the chiller gas temperature is actually 75. They are called high lift because that's how the systems are designed, the compressors are designed. There is in the market not much compressors that are available that will only boost the pressure to the extent you only want. So for example, if I'm only designing for air conditioning applications with a little bit of heat, I would say I only want a 25-degree lift. So I want 7 degrees or 30-degree lift, 7 degrees to 37 degrees.
No, but if I have to exchange heat, the working fluid must be at a higher temperature.
No, but you don't need it to be at 60. I can exchange heat, if my ambient is 40, I can exchange heat at 45.
The rate of exchange will become much lower.
So that's a design problem, but actually the bigger problem we have is that the compressors will still produce a much higher temperature than what I need to. So these are typically high lift compressors. Most of them are, whatever is used in the air conditioning, it depends on a pressure ratio as we call, and you need a pressure ratio of 3 to 4, and that's what I was mentioning, it's mostly a pressure driven system.
But today there are technologies of variable lift.
There are, yeah.
There are. So it is commercially it is available, very much it is available today. So at least in the HFCs or HFC space, it is available today. The variable lift. Based on the ambient, the discharge pressure,
it keeps on varying.
Yeah.
Yeah.
It is available.
Is this clear? Can we move on to the next topic? Next topic is with Kaushal.
So when we say
Components in heating and cooling and storage options. So we'll put the next slide for him. Are there 2 slides? Yeah.
so if you look upon all the system or components in a HVAC system, so one of them one of the most important component become the compressor. Obviously motor and controller has a separate section, and then we have TXVs or EXVs, then we have heat exchanger, and most of them are not being manufactured in India even today. That's one part, and you can see that what we have compressors almost 85% we are importing. That PCBs and controls become a part of motors and control, and a part of chiller control also. There is another separate controller, that one 80% of the components are imported. Motors 80% is right now imported. Heat exchanger to a good extent it is being assembled, but a lot of them are also being imported. Fans and blowers, so the fans and the blower mechanical parts are being mostly in India, but again when it comes to the motors and controller part, that's almost being imported. What are the technologies if you look upon that SMEs, small medium entrepreneurs are not much involved in that. PCBs and controllers is basically design skill is absent, complex supply chain, raw materials and magnets for motors and controller. Heat exchangers, what we are basically lagging a lot is in design capabilities. Fan blowers or any other subsystem, the advanced tooling process which can make thousands of numbers quite cheap. Those things are quite missing in India. So what we can do about that is, what is the session for this particular substation, question for this particular substation. So any suggestions are welcome for that.
I don't know, it's when I hear the talks by my NCPRE colleague or electronics people, so they have quite a few kind of BLDC motor, non-BLDC motors development which they are looking for this industry transfer. I think more than me, Professor Ashok Jhunjhunwala might be knowing some of the work by Kishore Chatterjee and VGF when they are talking with the MNRE colleagues. I'm not sure where, at what level and all.
Higher efficiency motors are, we are going to talk about it in the later part.
Okay.
There is enough available. Today enough motors and controllers are being designed which are efficient motor. But today, still compressors are mostly imported. So this is one of the tasks. We need to start making all of this.
So we do have the large motors, but mostly AC motors, which is some 20 to 35% efficiency range because of the variability on the process and the pressure what we make it here. But if you look upon the today's motor has to be 80-85%, 90% efficient, it's not available, and most of them we are importing. Even those motors are not very efficient one. Those itself are 55-60% efficient. Okay. So. The another thing what we were talking about is how we can go about 10 to 12 COP. So obviously we are not able to use heating and cooling simultaneously. So sometimes we require more cooling, sometimes we require more heating, and then the process comes, can we store it? If we can store it, obviously we can utilize based upon the requirement, and that's where the thermal storage comes in. That could be for both hot side as well as the cold side. Hot side we can again have sensible only temperature difference based, and then latent heat based like phase change material. And the cold side also we can have that sensible heat where the temperature difference only matters, and the latent heat based system where temperature remains constant, however phase changes. And this is really going to help us to achieve that 10 to 12 COP because we can utilize both heating as well as cooling. Material development for such, process development for such could be again question to be asked here. If any suggestions and other things that could happen. Low cost materials, that's the important part.
So two parts. One is motors and compressors. Now increasingly being understood, and we'll discuss that later on. And the second is storage. And we are talking about storage. For example, if it is a water, hot water and cold water can be easily stored. We can store the hot water in a geyser or a thermally insulated tank. Similarly, cold water can be stored. Volume of will be large if you want to capture a lot of heating and lots of cooling. And for that, we can do some phase change material. And we are designing out here the phase change material. So for example, a simple wax can be used to store heat. So the wax melts and it means it absorbs heat. It solidifies, it gives away the heat back. So we can, and the If you do that, the volume requirement goes down like anything. So we have been working on all these things now. Storage and storage with phase change. Similarly, in chilled water storage, we are using phase change material. Ice will be the ideal. Just convert water into ice, but you don't need to really convert. But for that, you need to go below 0 degrees centigrade. You can always create phase change material at 8 degrees centigrade or 7 degrees centigrade at whatever you want. These kind of R&D, if we do, we can also do the storage. Question?
Yeah, I wanted to know why compressors are not made. Why are we importing such a large percentage? What is the challenge?
Motors were all imported. Only BLDC motors have started getting made now. So there is.
Yeah, BLDC probably is a relatively newer idea. Therefore, it's not yet caught on. But compressors have been around for a long time.
It depends on volumes.
Exactly. So the compressors typically had a very high level of IP protection, patent protection, and there are very few people who are manufacturing those compressors. And particularly when you look at centrifugal, like for example, large systems, screw or turbine based, centrifugal based, very few people who had the technology to make them. It was controlled. And scroll based, for example, still Emerson was one of the leading companies who makes them, and now a few large companies are making them. Having said that, there is an opportunity. There are now designs and others that we are working on and others are working on. It really requires scale up. It's just like motors, compressors is another area where we have to develop capability, except the small refrigerator compressors that is being made locally and compressors for air conditioners less than 3 tons. Everything else is imported.
So again, it's basically the scale of operation, the business scale, the putting of factories and the profitability. So the companies especially look into the volumes, nothing else. If the volumes picks up, every company will invest. So all the products, today we have recip technology, like large recip compressors for refrigeration. It is manufactured in India. Screws, some of the Indian companies have started manufacturing. Centrifuges is mostly it is imported. Today nobody manufactures here. But screw, recip, and scroll is still imported mostly. So we have basically industry will graduate and we will start producing more in India for sure.
And there is also, as of now, there is also very few core design capability also in these areas in India. If you really look at scroll or if you look at centrifugal or anything, there is very few turbo machinery or advanced displacement machinery laboratories that work on them anymore. So if you go to any academic institutions, you will find very few people who are working on these kind of the core technology itself.
So the designs are available or
there are designs are available and there are developments are also available. So there is opportunity to innovate here. It's, as I said, there's no manufacturing scale yet that are available. So most laboratories have moved away from working on these technologies. And as we were saying in the earlier session this morning, the solar PV people, academics said we are there, industries are not there. Now possibly both are not there in this space. We may have to look at how we will bring everybody onto the table.
I'm from an industry, so I'm very open here. So most of this R&D happens in India. Only thing we are not manufacturing in India. Again, as I said, it is not because just of the scale. So skill set, depends on the company's like investment and long-term goals. They do have the resource today to develop and qualify the products in India, but it's only the manufacturing we are not doing. So.
Yeah, because the entire motor design team, including BLDCs, they sit in Hyderabad, Bangalore.
Yeah.
So you name it, whether it is compressor or
that is true. So this is anything. Corporate. I also worked in GE and I've been part of their compressor development team in the appliances space, which was then later sold to Electrolux. So it is controlled. So if you look at democracy, like for example in motors and controller, there are now a lot more people who are working on BLDC and academics and others working on that kind of diversification. You don't see. You do see large companies working like TEL. The TVS Group company, Turbo Electrical, there is the TEL. Turbo Energy, yeah. They work on these turbochargers, which is again a centrifugal compressor or expander combination. So there are pockets of research which is not yet made in large enough volume to apply to this kind of a market here.
So is there any clear-cut product requirements there in this space? I'm saying, like, if it is there, definitely we can do it because we have the necessary design skills, manufacturing skills, everything is available.
Certainly, I think we need to come together to define those specs. Essentially, what does it mean to design the envelope for an Indian operator?
And when you talk about the controllers, at least I know that many of my colleagues and friends, they used to design the controllers, and I was part of the localization in India. We developed all the pieces. Maybe some electronic active components we don't get in India, but other than that, you can do everything in India. You can do the testing, complete product development. You can do it.
Controllers, I do believe there is strong enough capability that exists. Of course, the basic electronic PCBs you still get somewhere, but controller capability do exist. What I am talking about is the core compressor design itself.
Okay.
What can we do in next 0 to 5 year, 5 year to 10 year, 10 to 15 years?
So broadly, if you look at it, this is what I've been talking about. What is in our hand? We already know the system intelligent management of the systems. We have Ankit who is working in ZP, primarily looking at continuously monitoring systems. These cooling systems are something that degrades quite rapidly. So really looking at it and making sure it is in the same design condition as it was. Efficiencies of motors, these are the two things that we are going to talk about a little later. The demand management, which we already said, by phase change material that Kaushal just talked about, hydrates and slurries that we are working on. And we are, from a thermodynamic perspective, improving the system efficiency by proper design of refrigerant. So it's a question of the refrigerant choice and selection that we are working with multiple companies like Honeywell and a few others who make these refrigerants. So this is the here and now story, and also from a heating perspective, we are looking at steam as a primary derivative of heat pumps, because when we want to do industrial heating with heat pumps, we cannot stop at 100 degree or 90 degrees. We have to go all the way to 250 degrees C, which is the biggest market in terms of small heating in industry. Almost all of process heating is up to these temperatures, except we go to mineral processing, which is cement, metals and all of that, that goes to 1000 plus degrees centigrade. So all of my typical consumer products and all other products is less than 250, and that is the biggest chunk of the market. So that is one of the things that we are looking at. Broadly, the next set of it is what we are looking to see. While I use electricity as an input, there is also a lot of availability of wasted heat that is available from high temperature processing and other kinds of applications. So thermochemical heat pumps are something that is being worked upon by many people. The second aspect is I cannot get to 250 directly by heat pump alone. I need an intermediate step, which is the steam compression, because I can do low temperature I can do low pressure steam. And when we want to go to higher pressure steam for whatever process applications, we do need steam compression system that will take it there. The Kobe Steel in Japan had done some pilot. They have demonstrated 160, 170 degree applications, but now that's something that needs to become a lot more common if we were to achieve the electrification of heating goal. The previous one, the third one I talked about earlier, which is the desiccant. Here, one of the design challenges is most of the desiccants that we know now, including the ones that is used by Thermax and others, require high regeneration temperature. It will absorb the moisture very, very easily, but it will not release it. And if it does not release it, then there is no point. I cannot use the material again. So we need materials that will release it at a low temperature. So we are working on some materials that can actually release it at 45, 50, 55 degrees, which is critical for us to do the tight integration that I talked about, where there is an absorption by a material and then the rejection can be done by the heat rejected from the heat pump itself. This alone, if we are successful, that contributes to a 5 times increase in COP. Not half 2 times or 3 times, but 5 times. Right now from a COP of 3.5 to 4, it gets to about a COP of 15. So that is where we are talking about. And compressor, I think we said you are already there, but still it's not widely used in many of these applications. I think that's something that we are looking at. Far out is a couple of concepts that people are talking about. One is solid state. So while we are still talking about vapor compression, there has been a lot of development that has happened in near ambient temperature solid state refrigeration, which includes magnetocaloric and barocaloric and a combination of that. In our lab, we do have some which is working at 0 degrees to 5 degree temperature cooling. The advantage there is there are no compression, there are no other high energy activities, it's only a magnet, and you move the magnet in and out of a material in and out of a magnet, and the cooling and heating happens based on the properties of the material. But the challenge is right now it's too expensive, it really involves a lot of rare earth materials, and also I think it's far out, and if it really happens, we are talking about 150 to or 1.5 to 8 times increase in COP of these systems. Material innovation is happening for passive cooling, while we talk about heating and cooling, particularly cooling as a chiller product from perspective, but it's actually a system which also, because you're cooling a space which is a building. So there are quite a bit of activity that's happening on coatings and materials that allows to reject heat passively. Right now we are not able to reject heat from this building directly because the ambient is the same temperature as the temperature at which we want to reject, or it's at a higher temperature, so we can't reject heat. But if you are able to reject heat to a lower ambient, which is outer space, typically much lower, and it is possible under certain wavelength conditions, it's what that approach tries to use. And seawater is something that people are looking at, and it's something that's gaining more and more traction. That's because that is one plenty renewable resource available across the world at depths of 700 to 1000 meters below the surface level. Water temperature is 4 degrees across the world except the polar caps. Now that is a big resource, particularly if you are able to do district cooling. But nevertheless, that's a heavy infrastructure project. So that's something, though it's technically not a technology development exercise, but it's an infrastructure exercise. So broadly, these are what are some of the areas that we are looking at. Probably I'm missing something, and maybe if some of you have heard or seen something that can contribute to anywhere between 5 to 15 times improvement in cooling systems efficiency, would be happy to hear. So here I think primarily there are just 4 things that we are looking at. No? We're looking at both active and passive cooling. Passive cooling is going to play a big role in reducing the demand for cooling. Materials like the facade design and all of that, and also combination of desiccants and all, and really looking at the minimal amount of energy that is required for cooling. Second is looking at cooling as a thermal comfort rather than cooling as a temperature output. So it's basically about thermal comfort that we are looking at. The solutions for smart control, and mostly technologies that have matured. TRL4 and above is what we are looking at. So this is what is driving our thrust towards this heating and cooling dominance, and broadly put together with these items that we want to drive, and those 4 parameters, looking at methods of both active and passive cooling, thermal comfort, integration of smart solutions, and TRL4 and above technologies. This one. So this is an example of how we had done one project on integrating the slurry, the phase change material as a battery. This is equivalent of a 1.5 TR and 5 TRH solution for a domestic air conditioning. Now imagine if you want to deploy solar PV on the rooftop, and primary demand in a place like Chennai is for cooling, which is mostly in the night. So what are the ways by which you can put it in? An example of storing it in the form of lithium-ion battery, and this is a previous study we did it with ice slurry. Now we have phase change material that is even better than this, which has even more efficiency. But with ice slurry, what we were able to demonstrate was an average cost of cooling, which is less than what I can achieve out of lithium-ion battery. Now the lithium-ion battery technology cost has also reduced. This was about 1.5 years ago, which we did, and it kind of gives you an idea on when we talk about renewable integration into the building, along with appropriate choice of materials that we want to use, we can get to a far higher RE integration without actually compromising on any kind of comfort that we need. And at megawatt hour scale, we are really looking at far lower capex, because this is a chiller. Storage can be as much as you want. It's only a tank that you need to build, and you can keep on generating the storage material, and the overall cost of it can be fairly cost effective as well. So it's as circular as possible in terms of the materials that we have used here. It kind of gives you an idea on what's possible if we are able to reinvent the whole concept of heating and cooling along with thermal energy storage, because it also enhances your ability to bring in more renewables.
So I think these two things that he has presented we can discuss together. Pretty much that will.
I don't understand. What is rupees 75 and 6 lakhs? What are those?
No, here it is rupees 75 the cost of cooling delivered overall, and 61 which is the cost of cooling delivered. On the right side is the capex that I had initially used. 6 lakhs was what I had to use, and 1.5 lakhs for the overall slurry generation system. Now that 6 lakhs was more from the market, right?
Simply say that
Just look at the
cooling as a battery. We are already implementing chilled water storage, chilled water or hot water storage, and using as a thermal storage. In fact, the research park has what's the size of the storage?
3 lakh liters.
2.5 megawatt hour of chilled water storage. So what we do whenever we have excess energy, because now we are getting solar and wind, so if we have excess electricity, we just chill the water. And when we have less energy, we use the chilled water. So that's something that we are already using, nothing very new. But if I look at the ESS,
This is the slurry phase change material
and we can now put in PCM. So all this is being done. So heating and cooling pretty much to some extent we have actually closed it. Now we like to have a discussion on that. Then we'll take a tea break, then motors and controllers. Does everyone understand what we are talking about? This is something very, what I'm pointing out, why the biggest question is there a totally fundamentally new technology that we are talking about? Frankly speaking. Why has this not been done? This is a question that some people have asked me. Because the oil was so cheap, coal was so cheap, petrol was so cheap, we didn't care for energy efficiency. Huh?
Demand is increased.
No, not because of that. I think the cheap oil, cheap petrol, cheap coal has driven the whole thing. If it pollutes, then it pollutes, doesn't matter. We can not even think of using electricity, think of using efficiency. All this will increase a little bit of cost. Essentially, the whole world has moved in certain direction for long. Now that climate change is taking place, GHG emission is threatening us, suddenly people are waking up. All over the Europe, heating is done purely using gas and oil. It is a gas and oil. Only this year, a few countries are saying new heating and cooling can only be done using heat pump.
That was driven by the Ukraine war.
By Ukraine war. In fact, that also was not because the price went up. Well, price went up, and also there was a lot of noise at COP. That Greta was making enough noise. What's her name? I don't remember. So, So I think gradually people are shifting. Is this very complex technology? No. But if we can imagine the kind of thing, can we at least start using heating, cooling in our homes, in offices, then in factories? I think this is the task. Why we are having this workshop? Over the next 5 years, 10 years, and 25 years, we need to really reimagine the world with energy efficiency. If we start reimagining the world and driving the world that we will use energy only efficiently, I think these are doable, and this is where India should take leadership. India should leapfrog. Before others are able to do it, we should just go on doing it. This will mean not following the rest. And it's going to be very difficult. Because 2 pipes, one for heating, one for cooling, is it very difficult? No, it's not very difficult.
today, right now, every house has 3 pipes.
So we will plan to implement it in part of our next gen stage of campus. Yeah. So, do we want to discuss this further? On the one hand, see, India is a particular, if what I did not present, our air conditioning usage have gone up like this. In last 25 years, it's gone up like this, and going up increasing. Earlier, only up, as a child, I don't remember ever seeing air conditioner. Forget about being in an air-conditioned room. That's not correct. Cinema halls, part of the reason we went to cinema halls was because they were air-conditioned. Otherwise, I don't remember anywhere going to an air-conditioned house. Today, air conditioning has become normal. Middle class is starting to acquire that. So, I think things are changing. We are still very, very early. So, at this stage can be very much. And that will mean change, conceptual change, mind change. Otherwise, we are caught in small things.
So, as a end user affected by climate change, okay, as you rightly pointed out, that is the main reason why we want to do this, not because of the growing demand. For that, we need to demonstrate different technologies like cooling, air conditioning plus heating as a one topic you mentioned. But there could be houses, for example, in my house, we don't use air conditioners much, like other than the peak, maybe 1 month or 1.5 months. So in that case, we should also demonstrate standalone heat pumps kind of a thing, so that again, on increasing the energy efficiency point of view. So this needs to be marketed well at different forums, and today you as an institute you are doing a good research, but for example this has to be a scalable format. We need to
make products.
Yes, exactly.
And we need to make products. We need to, of course, demonstrate the product.
Yes, exactly.
And then use it. Now, there will be places where I may not be able to use 100% heating and cooling.
Exactly.
It doesn't really matter.
Yeah.
When I'm talking about, I can design the system to a COP of 10, then effectively, even if I get 6, as opposed to 1.2 today, it's a huge gain.
Yeah.
Even if I get 5, I'm very happy. I think let's move in that direction. Otherwise, we'll keep on talking caution. I think early gains can be made, products needs to be designed. We need to put it, show it, demonstrate it. It should not compromise on our ability, comfort. I think things will happen.
Yeah, there are district cooling.
A hot water pipe in my kitchen, which is a clean RO water, which I can use for cooking. Now, it will change the cooking. But frankly speaking, we will never be able to get out of LPG based cooking, because LPG based cooking is so much cheaper than electricity. But if you have a 60 degrees centigrade hot water in the kitchen and you will use it every time you need to heat, and use this induction cooking, I think electricity is better. We will shift it straight away. Otherwise, for all time, it will be LPG. I think it requires a little bit of effort. We are talking from research park, not just from IIT. Sure, IIT and IITM research park, where we are talking about translation of technology.
Yeah, so
thinking, conceptualizing, and doing this. This workshop, brainstorming workshop, is very clear. Do we decide to take leadership in the world in this? Then how many? We don't want intelligent comments. Say I am ready to work on it. Good. I want to know how many people are ready to work on it.
Yeah.
Well, of course, not now we'll discuss in the conclusion.
So
that's what it is.
So my only point is that we should be, the designs of the system should be tailor-made for different industries like residential, industry, commercial.
Everything.
And
those are matter of details, sir. And those are obvious things.
Yeah.
Okay. From, let's say, IC engine motors and controller, and will be presented by Kannan Lakshminarayan. So 2 slides, one slide this and this slide. You can.
Which is slide number 1? I don't know.
This is slide number 1.
This is yeah. So, yeah, as Professor Jhunjhunwala just now said, 46% of the world's energy seems to be agreed by different data points in the world is consumed by motors. But what this doesn't account for is fuel that is burnt in IC engines that will also become electric, and a growing population of drones, robots for industrial as well as domestic, all of which will become increasing new segments which are powered by motors, which will consume electricity. So actually this 46% is going to increase rapidly, and in the earlier part of the session we talked about heating and cooling, where also instead of directly burning fuels, if we move to heat pumps, there again the claimant on energy is going to be motors. So I see this as something that will be a growing percentage, which means that we have to address how the motor performs. Of course, very broadly we are looking at improving the efficiency, but improving the efficiency is not only about saving the energy in the process, but it has a lot of other adjacent benefits. Your thermal management system will become simpler. Your
The reason is all the loss of efficiency eats up the motor.
yeah.
So the motor overall gets heat up. Thermal management is supposed to keep the motor at a constant temperature. So we will be able to more easily manage thermal.
And that again means that you can run it uninterrupted for longer durations of time without it tripping because of overheating, and you can keep the appliance etc. well enclosed, which means it is protected from the elements around, and it also becomes then easier to maintain. And finally, for all things we are concerned about backup power, and that will become more affordable if the efficiency is higher. So this is broadly the overview. And almost, actually, Mukund will be taking over in the next few slides. Only about 3% of all the motors, correct me Mukund if I am wrong, are today of the new generation type which are energy efficient. All the others are of the older topologies that are much more inefficient. So the room for improvement is phenomenal across different application areas. So that's
Just like motors and heating and cooling, we present in a very simple manner that it takes. What is the reason why we can make motors and controllers most efficient? Historically, when electric motors, we are talking about electric motors and controllers came in, what we really had was the electric power from the grid, 230 volt, 50 hertz AC, 50 hertz, 60 hertz, air conditioned, sinusoidal wave. And this is what needs to be applied to a motor. So all motors were designed assuming the electricity is available only in sinusoidal form at 230 volts. That's the way the induction motor, for example, had come in. As electronics grew, in the first phase, while the electronics really gave us a lot of gain, but electronics was not a 24/7, something could be used for 24/7. You could use it and you have to shut it down and again turn it on, and it was not something at a very early stage. We didn't have therefore anything which can run all the time using electricity. Gradually, as the electronics gained more and more common, we started thinking of putting, for example, Ethernet hubs which will run 24/7, base stations which will run 24/7, and all of that happened because of digitalization. And processors are coming in which essentially say we don't need to run everything at the same, depending on what is needed, you can increase, decrease, and it can run on a battery power instead of a 230 volt AC. As digitalization took place, you could start playing with electric field, magnetic field. Till that time, till the digitalization took place, till you learned how to do programming of electric field and magnetic field, you could not do that. Even in around 1990s, when this concept was starting to emerge, the problem was processors were not powerful enough to be able to manage the electric field and magnetic field at the rate at which it will be required. It is only when digital signal processors started coming, which is essentially till that time a multiplication would take something like 100 cycles, addition etc. could be done by one cycle. As digital signal processors and other co-processors came in, you could actually do multiplication and therefore division in a few cycles. As the digitalization happened and electronics became reliable 24/7, and as the processors became faster and you could control it by software, you started thinking of complex algorithms. Yet the key role that changed all this is a device called MOSFET. Till MOSFET came in, you couldn't switch on and switch off things rapidly. The first gain of this was realized at the turn of century. If you people remember, if you had an early mobile phone and used to get a charger for that mobile phone. The charger for mobile phone used to be heavy and big size because it had you are trying to do AC to DC. The only way you are converting AC to DC is 50 Hertz transformer. The 50 Hertz transformer, step down transformer to take the voltage from 230 volt to 5 volt or 12 volts and things like that. The 50 Hertz transformer will be very big in size. It's around turn of the century with MOSFETs coming in, we sort of say, well, we will not do something like that. We will just convert 230 volt AC into directly DC and then use a MOSFET to switch on and switch off, and then use a much higher frequency. From 50 Hertz, we started talking about 5,000 Hertz and 10,000 Hertz, 100 times higher. If we do 100 times higher, the transformer requirement will go down by 100 times. I remember this around, many of you are just still very young, so probably won't remember. That's around the turn of century, we started doing this, and we said we can have a very small Kuti transformer, Kuti chargers, and then there was no stopping. MOSFETs, and then even more higher power, the IGBTs and other devices, the power electronics which enabled us to do this. The power electronics cost, integrated circuits started coming only around the beginning of the century, and by around 2010 or so started getting used everywhere. Stage was set for the next big revolution of trying to completely change the motor and the controller. And this is where people like yourself, Kannan, all stepping in and started playing with algorithms. And we said we can do algorithms, digital algorithms, to do the control that we need. I think what I want to point out, That made BLDC motor possible, brushless DC motor possible. Around 2011-12, costs came down by 13, 14, 15. Still a big problem that it is using a permanent magnet. I'm sorry I'm elaborating that to set a contest. Permanent magnet, which of course almost all permanent magnets are controlled by China. To that extent it is going on. The R&D has shifted from there to no longer for brushless DC motor, but motor without any permanent magnet. And that R&D has shifted. Almost every PhD student who graduate from here today is working on the next generation motor, which is going to go beyond BLDC motor, which will not have a permanent magnet. As of now, the sizes are big, the efficiencies are not great, algorithms are complex, but they are very early generation. But we are starting to see very, very good algorithms which will be implemented over the next 3 to 4 years. Stage is set for a totally different kind of motors and controllers. And I think that is what is going to result into what we are really talking about. Giving far, far higher efficiency, far lower cost, electronically controlled motors and controllers. That's what it is, and we want to. If you have understood this, fine, we'll go straight to next section. Otherwise, we will discuss this. Questions? I remember the first time when I saw the transformer for charger going from here to here. That's the time I started understanding the power of power electronics. Today, very, very light, something like this, is a 400 watts charge. Unbelievably light.
Before the televisions used to take 2 minutes to boot up.
Yeah. Radios. And you needed to put the tune so that radio could be auto-tuned to that. Those are vacuum tube days. Any questions? Or we straight away jump into more details on motors control? I think we straight away jump into it. Mukund, your turn. Yeah.
As we say, the power electronics and the permanent magnet motors, the power electronics and the permanent magnet motors are just coming in. Do we expect
they have been there for 7-8 years now. 6-7 years.
Do we expect it to see this get into a lot more devices, including the current set of motors, the larger motors, or we are really sticking a smaller motor? Because most of the
I think next slide has that. Mukund, take over. Motors and controllers. Kannan and Mukund together can present what are the opportunities. And get to the next slide, please.
Good evening to all. These few slides are principally stemmed by Professor's drive. When I met him first, he said, look, I want you guys to be a part of a team which will contribute to something from India in the motor and controller space globally. And I've been in motors and controllers for the last 3 decades. We set up a plant in India with the team, and we exported about almost 400 million motors and controllers out of India, and out of which about 30% were going to China. And at that time we had a capacity of motors that we set was 50 million per year. We started with 1 million per year, went to 50 million per year, but that was not enough because China was making 10 million per day. Just 2 companies in China were making 10 million motors per day. So that's the kind of scale which is in the motor and controller space. So coming back to some global statistics, if you look at it like Kannan mentioned, Prof mentioned, half the energy that is produced in the world is consumed by electric motors. And interestingly, I want to go one step further on this statistic.
Half of the electricity, not world's energy.
Half the?
Half the world's electricity.
Electricity.
Not energy.
Correct, you're right. Yeah.
We are not allowed fossil.
Yeah. And this is again a thumb rule based on what we have understood from various discussions. on an average, a world motor works at somewhere between 50 to 55% efficiency, based on the fact, like Prof mentioned, that you used brush motors, which were between 35 and 65% efficiency. You used universal motors, you used induction motors, and you used motors which were not brushless with the use of MOSFETs and power electronics. So on an average today, if you look at an efficiency of your motor, weighted average will be of the order of 50%. And the opportunity today that's available is, by maybe 5 years, 7 years, or 10 years from now, it may be quite appropriate for us to make a statement that today an average motor efficiency in the world is 75 to 80%, which means that there is going to be a 60% saving in the energy in the world of motors in the next 10 years. And I'm coming down quickly to one of the topic which Prof mentioned, 2011, 2012, he started working on brushless DC motors for ceiling fans. It's a very interesting statistic, and Sarana Chandran, our CTO, and the power electronics champion that we have, India has got 1 billion ceiling fans running. 1 billion ceiling fans running. Back of the envelope calculation is that one ceiling fan uses 1 unit of energy per day, which means 1 billion ceiling fans, they consume 1 billion units of electricity per day. And it's a very low hanging fruit, driven first by Prof and his team and then by Government of India, BIS, BEE. Since January 1, 2023, Government of India has announced that you will not be allowed to manufacture or sell any ceiling fan which is not a star rated fan, and preferably it should be a 5-star rated fan, which means every ceiling fan will save energy by 60%. Mathematically, against 1 billion units of energy being consumed per day, the ceiling fan space will consume 400 million units of energy per day. So theoretically, 600 million units of energy saving per day will move the country's needle on energy, and by again a back of the envelope calculation, it works out to something like 200,000 gigawatt hours of energy per year. And I'm sure all of you know that Kudangulam last year produced 12,000 gigawatt hours. So you can see the magnitude of the energy saving that can happen to a nation like India just by converting the induction motors in a ceiling fan in India to brushless DC. So that's the kind of power. Is my communication clear? The numbers, I hope the numbers are registering because these are huge. Huh? So getting back to a statistic which I think we've been working with for quite some time. See, the overall global market for electric motors is about 150 billion US dollars, which are used in industrial. Industrial is about 30% of that. Automotive is a very interesting space where we have exported about $1 billion worth of motors in the automotive sector globally, because on an average, a world car has about between 35 to 40 electric motors. So the automotive industry alone globally consumes anywhere between 3.5 billion to about 4 billion electric motors, be it for your under the hood, be it for safety, be it for comfort, be it for convenience. Interestingly, if you take a high-end car and you sit in the cockpit, the driver's cockpit, from the power steering to the seat to the window, all put together, just the front seat, the driver's seat, will have somewhere between 30 to 35 motors in a fully loaded car. So that's the kind of population which is there, and this was the average motors per car in the early 90s used to be about 10, and today it's about 35 to 40 electric motors per car. So it's a huge space, automotive. Appliances, I don't want to go global. A lot of discussion has taken place, but I just leave one statistic to all of you to ponder about. India as a country, we as consumers, we buy appliances, 160 million electric motors per year through appliances, be it your table fan, pedestal fan, ceiling fan, be it your dessert cooler, be it your refrigerator, air conditioner, dishwasher, be it your electric chimneys, be it your washing machine, all the appliances which we have around our house and kitchens. Today India buys appliances which have 160 million electric motors per year. So that's the kind of space that appliances. Pumps and compressors, we've heard a lot. Computers, I'm not going to cover too much. Aerospace to toys, I'm not going to cover too much. But this is another area where I think, Prof. Kannan, I would like you to keep it at the back of your mind, because there is a prediction done by a leader in the world in the BLDC space. It's a company by name Nidec. And this company was started in 1970s by a gentleman called Nagamori. He is the most respected man as far as BLDC space is concerned. And he has made a statement, a prediction, that by 2035, the population of service robots in the world will exceed the human population. And I firmly believe that. I firmly believe that. If you have some time, I request you to Google a site where Google for World Robotics Conference held in Beijing in August 2023, and it's mind-blowing. And it's absolutely mind-blowing to see all the robots in action. And again, a back of the envelope statistic is, we made an analysis. On an average, that the robots that you see over there have anywhere between 4 to 18 servo motors per robot. 4 to 18 servo motors per robot. So this is going to be an explosive area. So Prof, I would like to leave a thought in terms of if we can create a cell for servo motors and the alternate to servo motors which are used in robotics, that will be a huge opportunity for India, because there are very few players, largely Far East Japanese, who monopolize the market. And to give you again a commercial statistic, if you take a 100-watt BLDC, a 100-watt BLDC, assume it costs 1,000 rupees. A 100-watt servo motor, I'm told, costs 20,000 rupees. So that's the kind of monopolization that people in Japan have. And so it's not at whatever price they quote, you have to buy. There's no choice. So it's a huge opportunity, not only because of the explosion as far as the market is concerned through service robots, but even the existing market, the price and cost parity, if you look at it, the price is about 4 to 5 times the cost. So 70-80% margin item.
What makes the field of motor control interesting is the fact that earlier generation motors were operating at a fixed speed and a fixed torque. When you're talking about electronically commuted motors, you're actually talking about software driven motors, where you give all degrees of freedom to the motor. And by doing so, you basically improve the application efficiency, and in the same time, you also reap certain efficiencies out of the motor itself. On a motor footprint, the points to consider would be, on any given motor, you would have core loss and copper loss. So, actual motor design is defined by its power density, as in for what quantity of active material, how much power can you produce. So thereby you select steel, copper, aluminum, housing, etc. And on control, based on the motor geometry that you adopt, you basically have to manipulate the electric field. I would like to put it as the currents that you inject into the motor to, in a way, interact with the magnetic fields within the motor to produce the desired torque and speed characteristics that are expected out of it. The whole of motor control is about achieving this cohesion between the current that is pumped into the stator windings versus how the magnetic fields which are created within the motor operate. And that basically brings out the speed and torque use cases that you require out of the motor application. And by putting the design and the control elements together, you can address any application. I can give a couple of examples. If you look at your kitchen, you have a mixie, you have a blender, you have probably a food processor and a grinder. All of them operate at various speeds and various torques. When you move into a software driven motor, you can build one product which serves all these requirements in one shot. That is what a software driven motor is all about.
I think there is one important point which we are still learning. As mentioned, power electronics has given us power electronics and processor driven power electronics has given us immense amount of ability to play. But I think an area which we still, in its very infancy, only very few people understand it well, is the magnetic field management. I think magnetic field suddenly comes far more. It is not, you are certainly talking about coils and you are talking about materials, magnetics, and it is still something, I would say, still in very early stage. So you will see a lot of changes coming in the coming years. I think basically beyond that, they have already said. We need to keep that in mind. We will, it is not just the controllers, but the motor design itself will significantly change over time.
Point. When we talk of magnets, we are talking normally about, say, rare earth or ferrite or other magnets. The elephant in the room is the steel itself, which is a temporary magnet. For cars, we did a benchmarking. My team did it 2-3 days back. We found that 85% of the loss in the motor is coming from the steel, very little from copper. It's a killer. So just the steel lamination, which is a temporary magnet, is itself something which is in need of a lot of improvement.
Can you explain that a little bit? I mean, I didn't understand.
See, the steel that goes into the stator, rotor, etc. is not a magnet. Only under the influence of the current, it becomes temporarily magnetized. When you switch off, it becomes demagnetized. So it is a soft magnet, that's what it's called. And because it is getting continuously magnetized and demagnetized during operation, it generates heat. In normal applications, we think, and it's true also, that contribution to losses is very small. It is the current going through the copper, which heats up the copper, which is dominant. But I found that in electric cars, the moment you go to somewhat higher powers, where power is achieved by going to higher speeds, this is so dominant. And the numbers were really surprising. Simulation also bore it out, calculations also bore it out.
You have two components in a motor. One is the stator and the other one is the rotor. In the stator, you have coils of wire through which current passes. Now, there are flux lines that are established in the stator, and as the motor rotates, these flux lines have to change their orientation. And because of memory effect and resistance to change, they take some time to reverse. And this is what you call as the hysteresis in the core. And that reversal, that energy is what makes the motor heat up. And then if that stator is contained within the rotor, then like for example in a hub motor, the rotor is rotating outside and the stator is inside. You need to evacuate that heat. You need to bring that heat out, and you have certain challenges there as well.
And to complement to what Kannan said, up until 10 years ago, most of the electrical grade steel, silicon steel were of 0.5 millimeter or 0.35 millimeter thick. And the moment they started electric vehicle motors, Japanese people started looking at thicknesses of 0.05 mm as compared to 0.35 and 0.5 mm. So that's the magnitude of losses they were trying to avoid by reducing the thickness of the electrical steel.
So I was calculating 1 billion fans saving 60% of energy a day, consuming 1 unit a day, was coming out to be 200 terawatt hour a year.
Yes, sir. 200,000 gigawatt hours.
Yeah, 200,000 is 200 terawatt hour a year. So that's in fans itself. And yes, I mean what he said is true. I actually started this BLDC fans in India, that solar DC system, which he had by the way designed the fans. I didn't realize that. More by accident, because we wanted solar to have very little power, so we wanted to save power. So somebody came with DC fan and BLDC fan. We started using it. But come back to this. I mean, this is the area we are getting it. This, just 1 second. 2-3 things that are very important. First of all, it's an opportunity for India to become a player, big manufacturer of motors and controllers. By the way, China has already started doing it. It's not that, but yet I think there is enough play going forward. Once those algorithm kicks in, we still can take significant amount of leadership if we really put our mind into it. My fear is even the academia is not taking enough. They are just used to doing some minor problems, not really going all out to try to do that. Number 2, huge contribution to this reduction in GHG emission. So I think huge opportunity, and therefore in taking India to leadership, both for heating and cooling as well as for motors and controllers. It's up to us to take that up. Satya, this thing is there.
2 questions. One, on the scale of these motors, like most of these we are talking about, when the list I look, except pumps and compressors, everything else looks like small motors. So is there a constraint on the size of motors that we are discussing here?
They're all making, maybe you should speak the number of motors you are looking at.
No, I'm talking about the rating of these motors, kilowatt or megawatt rating of these motors.
No, we are talking about tens of watts, maybe a few watts. The fan motors are now 30 watts.
No, the flip side of it, will we have a constraint in when we say we want to design a 2 kilowatt or a 3 kilowatt motor?
No, it will be better.
Better.
Okay. Easier, and as we go higher, it is easier.
And the second part is, does the same framework apply to generators as well? So
yes, very much.
So as we work on these
motors, controllers and generators are same.
Okay. As we work on these heat recovery and other projects, we do see a big need for generators as well as.
But and you both. You can see. Yes. Speak in the microphone.
Yeah, I was just telling him that higher the wattage, you could work around the motors without use of permanent magnets. Like there is a break even for your EV motor is what, 5 kilowatt is it?
7 kilowatt.
Yeah, at 7 kilowatt, the switch reluctance motor, which does not use permanent magnets, is about the same in terms of cost and performance and economics in the EV motor.
Easier to do higher. I think let's move to the part 3, and because that's also equally important, and then we will get into a more detail. Manufacturing in India. Focus.
So I think this is a superfluous slide because I already covered these. I just wanted to put this on slide because Sarvana Chandran, who is a power electronics champion, I have told him that out of the 50 odd solutions he's developed, focus on 5 areas. So these were the 5 areas which is there. Yeah, we spoke about. Here, yeah, this is very simple copy and paste. Yeah. This is a very simple copy and paste of what China did to build 5 million motors per day and make good money. So, design, development, including proto and pilot validation, tooling build, component manufacturing, sub-assembly processes, motor and controller assemblies, application integration and manufacturing lines and processes across the value stream. Ideally, all these guys who are doing millions per day, they have this all under one roof. We tried it in India, but we weren't very successful in terms of getting everything, where some portions were there, some were not there. We were depending on Japan, depending on China. But the ideal model, Prof, for it to be a business case for people to make an investment and get a good return on investment over a 5-year period is to do all this under one roof. So it's just a copy and paste of what China does.
Why would you say that? I mean, I'm just trying to understand. Why does it have to be one roof?
Basically, the drivers answer are two. The first one is nothing to do with economics, it's time. See, when you have a company that does the design and development and the company that does the tool build, as against both being done desk to desk next to each other, if it takes a week, that will take 2 months. It's a simple,
but for one company to do all of the 7, does that not require like a lot of different competency?
That's exactly what's being done by the Chinese.
No, it's all right. I think this is
one.
Fine.
And second
So-
one is economics.
yeah. So I think
There's no margin on margin.
no, I think let's not get into this. I think the focus should be number one, both in motors and controllers as well as heating and cooling. There are opportunities, major impact. What is most climate change conferences and climate change discussion, these things won't come up. It's very surprising because when its magnitude is so big, that means it is an agenda being set by someone somewhere and the world follows. It's an agenda being set up by the West. This is the real crux. I really think that climate change does not make technological without getting into both motors and controllers and heating and cooling. And what we want to talk about is how can Indian scientists, Indian technologists, Indian industry take leadership in this area. And this is what the brainstorming is. Fortunately, I started with Kannan, we got pretty much all these things. Kaushal was there, so learned a little bit about heating, cooling. And Professor Satya I got to know and I saw that. And then Mukund and Saruna. I think between the 5 of them, we have the core. We can keep on expanding. But I really feel this is the area where a lot of youngsters should work. I think we really have to go places. And the brainstorming was designed with this in mind. So, see, Sarun is one of the most knowledgeable person, and you should have seen his expression when he understood heating and cooling. First time he understood what it means. The first time you really understood it, no?
Yeah, and he said it.
Huh?
He said it also.
So the point is, just imagine. And so little understanding. Nothing magical about this. What we have presented in last couple of hours here, nothing magical about it. But we got it. And we have the base between IIT Madras Research Park, between the industries around here. I think we have to take leadership. Beyond that, frankly, I mean, I did what I can and I'll keep pushing. I'm not going to stop here. But we need several more people. We wish more, in fact, I see 60% of the people here are people who are already working with us, are younger people. I wish more people participated in this. Being at the fag end of the 3rd day, it kind of didn't work out as well, but it's okay. We probably will have another workshop in this area. But I want to quick questions and then discuss what to do. Yeah.
Yeah. If we want to push this forward, like what do you think are the first 2 or 3 things that we now need to do, now that we have all of the core group and the rest of that? What are the things that you think we'll need to do in the next 3 months for this to actually take off the way you think it should?
My question is more on a slightly different note. I think most of the presentation focused on the BLDC motor, where there was a need for a permanent magnet, whereas the magnetic material is something we don't have. So what do we do on that?
I think we are clear that you will start with BLDC and move to magnetless motor.
Okay.
So permanent magnetless motor. So that we are clear, we need to do. See, what do we need to do? We need to excite in the beginning 10 mid to senior level people. I am seeing here 5. 1, 2, 3. I won't say Mukund. Mukund is like me, more management. Is it okay, Mukund? Huh? I think I see 4 people out here. Kannan, Sarana, Kaushal, and Satya. I think this 4 has to become 10 at this level. That is the first requirement that we have. The 10 then has to prepare a more larger, 10 has to be fully committed and working more or less full time onto this. More or less full time. I'm not saying that you can't do anything else, but more or less full time. Then from this 10, we need about 40 others who will start working in this direction. I am talking about people at this kind of level. They are all, I'll say, mid-career. They are not 20s. They are not 60s. They are more like, most of you are probably 40s. Maybe somewhat older, somewhat younger. We need 500 youngsters to work with. For these 10 people, maybe 200, 150, 200. And for the remaining 40 people, another 200. So 200, 200, 400 plus 50. So that's a kind of people that we require. We need, and Rima has gone away, I will say to begin with 10 crore rupees of money a year. 10 crore will be. For the all, I'm talking about for the 10 people, not for the 40 people. They will require more. But 10 crore rupees money sitting out here trying to drive these things. Some is being generated, I'm not saying manufacturing, etc. is going on, but 10 crore rupees. The rest of it, I'm not saying 10 crore will do this job. Much more will be required, but much more will be generated by the industry and all. But I think 10 crore rupees of free money, ideally, we would like to have maybe in seed or something where we can kind of drive many of these efforts without any problem for the first year. I have a basic commitment from NASCOM. I would like to invite the leadership. I think we need to sharpen this, both heating and cooling, and this is a very good and basic commitment from NASCOM. I went to NASCOM and they all accepted that this is a major area where we want to become world's number 1. I think beyond that, yes, already Mukund is doing a lot. His team, along with Sarana. Kannan needs to gear up a little bit more with our friend in Bangalore. Satya is doing a lot, he's trying to set up. But I think I'm not talking about money for the companies. Those things are separate. I'm talking about 10 crore rupees out here driving R&D, getting the people, getting this 4 to 10 and support, and 10 and 200 are youngsters. And youngsters are people like that. I don't think and train them, do that, dedicated and I think in 5 years we'll make a significant, specific, yes, we have to, as somebody pointed out, we have to set up a demos, we have to, my feeling is we require in every area. We require in power electronics, we require somebody who understands magnetism well. The only person here out of these 4 people who somewhat understand is him. Heating and cooling are both Satya and Kaushal understands well. Power electronics he understands very well. So I think that's a core. We need 10 and that's what we need. And I put 10 crores as a beginning, then we require more. But that's what is required for this. If you ask me. Specifically, yes, we'll have to put demonstrators, we'll have to put this, we'll have to keep driving. He's already driving fans, very clear. Other appliances, Kannan and his company is driving it. Heat pumps he's trying to drive. But I think, how do we get 6 more people as committed? Clear technologists. These are all technologists. I'm not talking about people like Mukund and me, who probably understand as much and can drive things, but cannot drive now specific technology.
What should some of these students be learning or getting themselves into?
Well, I think there are, let me tell you one thing. When I joined IIT Kanpur, electrical engineering was not known. In fact, everybody said, why are you going for electrical engineering? And some people said, no, it's going to be a very important future, and I joined. And within a few years, electrical and computer science did play a dominant role. And has continued to play a dominant role over the last 45 years. My feeling is 5 years back, things have changed. Today, the two engineering I will consider the most important. One is a chemical engineering, another is power electronics. These are two very, very important areas where our best students don't go. Chemical engineering was a lot of whether it is for a climate change, whether you're talking about batteries or you're talking about hydrogen, or you're going to talk about many other things. The carbon capture, all of that is going to come from there. And the power electronics is going to play a very important role. I still feel power electronics is getting very sophisticated in terms of algorithms still, but magnetism is still not there. Power magnetism is still peripheral. So these two areas are going to play a very, very important role. So to the young people, keep that in mind. Of course, all processing and algorithms will play an important role. All those things can be taken for granted. Computers and electronics and all those things can be taken for granted. To the youngsters, that's what I'll say. These two areas are the most important areas.
Just to give you a brief, I've been in the power sector for the past 32 years. I've done thermal, gas, wind and solar, and now hydro also. What is worrying is in the last 3 days that we have gone through and the amount of power that we would require, and especially today's workshop on motors. The worrying factor, I think one more thing that we have to worry is about where are we going to get these copper from? For because we are already spending so much on the import of copper. Just to give you a statistics, 2018 the import bill for copper was 1,900.
Please, can you hear him? That's a very important point. I couldn't think about this.
So, just to give you a perspective, in 2018, the import bill of copper was 1,900 crores, and in 2022-23, it was close to 11,600 crores. We are just going to increase the import of copper. I mean, it's definitely not going to reduce. In whatever field that we are talking about, that is one area wherein we'll face problems everywhere. You talked about scaling of motor manufacturing, you're talking about power. Anything that we do, copper is going to be a pain point.
Not just copper, aluminum as well.
Yeah, I'm just taking one of it. There are others, obviously.
Raw material is the biggest issue.
Yeah, I mean, I'm talking about the import bill, which is going to affect us.
Yeah, just want to say thank you. I think it's been a long couple of days, 3 days. Feels like a couple of months for me. But thank you all. I think this has been, such an exemplary experience. I think I missed out on the first 2 workshops because I was on top. But I'm hoping to catch up with all of them. We'll have videos on all of these, so if anyone wants to, get a copy of the presentations or watch some of the videos, all of it will be available. So please reach out, and otherwise just thank you to all of our guests for coming and sharing your insights, thoughts. We wouldn't be able to sort of put together this rich program if all of these, top-notch scientists, researchers were not here. So thank you very, very much from, my team, IIT Madras Research Park, IIT Madras, and all of the people that have, been here to put together EnVision. And I don't have anything much to say about it. Uploading the videos. Yes, all of it.